Hey, good morning. I think I'm right here. Is it time? Almost. All right, it's 9 o'clock. Good morning, everyone. So we're going to be transitioning away from what we've been doing, which was finding antiderivatives, right? Using all our different techniques of integration. Everything we've been doing, good morning, up to this point has been trying to find the antiderivative of some function, and then we get some answer, capital F of x plus c, right? This is what we've been doing, right? Remember this right here, this is called an indefinite integral. I talked about this when we first started talking about it. I said, don't worry about where this symbol comes from, we'll get to it, right? But we're calling it an indefinite integral because our answer, even though we do get a function, because we have a plus c, there's actually an infinite number of functions. And so it's kind of like an indefinite. We're not completely sure exactly which one it is, but it's at least this family of functions. Today what we're going to do is we're going to shift gears and we're going to study something called the definite integral, okay? And the only thing that changes in notation-wise is that instead of having this integral sign by itself, we're going to add a number on the bottom and on the top. I'll explain what all that means in a second. And so we add these numbers, these are going to be called the limits of integration. Again, I'll explain that later. But this answer is no longer going to be a family of functions. This answer is going to be a number. And that number is going to represent to us something, all right? So we'll have to figure out what that is. But just wanting you to know we're making a big shift in gears here. We're no longer doing all those techniques to just find antiderivatives. We're going to go do something with it now. So I have a lot of things to show you on the projector today and on the TV. So I'm going to dim the lights just a little bit. I don't know how this is going to come out on camera, but just be warned, it may not come out that great. Yeah, let's just turn them off. Okay, so the fundamental idea here is that if we have a function, all right, this is our blue function here. If we wanted to somehow try and find the area below that function, all right, the area, below the blue, down to the x-axis, we can see that that shape is not, it's not like a triangle, right? It doesn't have straight edges on all sides. So we don't really have a formula for finding that area, right? There's no formula we have. So the question mathematicians asked is it possible for some arbitrary function to be able to calculate that area easily, right? And the first attempts at trying to do it were to use approximations, to just approximate what the area would be. For example, look at this blue, right? Do you think that this gray box is a good approximation of the area? Not very good, right? Not very good. In fact, when you look at it, right now I have the computer calculating, I don't know if y'all can see it says 100. That is the area of the gray box. And the 41.33 is actually the true area below that blue curve. Okay, so we're way off, right? So one thing we could do to get a better approximation is instead of using one rectangle, we could use two, right? We could use two, like this. What do I mean by two? I mean two rectangles, two gray rectangles. So what I'm doing here is I'm cutting up, from here to here, I'm cutting it in half. I'm looking at one rectangle here. Now, how did I determine this rectangle? Well, what I did was I went to the right endpoint, I plugged that point into the function, and I got how high it is, and then I just went straight over, straight down, and then that's my first rectangle. On the second rectangle, I went to the far right endpoint here, went all the way up to the function, then just went over and down. Now I have those two, right? Do y'all see that's a better approximation? Right? Now we're at 68.00. That's closer to the true area of 41.3. What would be even better? More rectangles. Maybe 3 rectangles, right? That's better. You see, every time I do that, I'm getting less error, right? I'm getting less error. You could say that the error, E-R-R-O-R, error, is going to be this and this and this, right? That's like too much. We're overcounting on that, right? But the more rectangles I put in here, the smaller and smaller and smaller and smaller and smaller and smaller and smaller the error gets, right? And do you see that I get closer and closer to the true answer? Look at where I am. Right now I have 22 rectangles, and it's 43.53. The true area is 41.33, right? So how many rectangles should I use then to get the best approximation I could ever get? 100, 1,000, 10,000, a million, a billion, a trillion, an infinite number of them, right? An infinite number of them. Now, can we deal with infinity in calculus? Yes, we can use limits, can't we? What we could do is we could figure out, okay, can we come up with a formula that would calculate the area of not 10 or 100 or 1,000, but a formula that would calculate the area of n rectangles, n of them. And then we let n go to infinity. And that should allow us to get an answer. But that's probably going to be pretty challenging, isn't it? To come up with a formula, maybe? So let me see how far I have my computer go here. I'm going to go all the way out to where I have it stopping. I have it stopping at 70 rectangles. And it's okay, right? 42.02 is still pretty far off from 41.33, right? Wouldn't you agree? But it's way better than my first approximation, which was 100, right? Okay, any questions on the fundamental idea? The fundamental idea is, can we somehow come up with a way to somehow figure out a formula that would give me the area of each rectangle and then add those up, sum those up, and let the number of rectangles go to infinity, right? That's the concept. Now, I've been debating this since we ended class last time, how I want to approach this. I've been teaching calculus for over 20 years, so I do it the same way each time, but I want to try something different this semester. Is that okay? Now, what's important to take away from this is that the way I'm going to explain it is going to be new, but what you wind up doing at the end of it all is I just give you a nice result, and then we just use that result. What I'm trying to do is present where the result comes from in a different way, all right? At the end, we're still going to use the same result, all right? And what I'm telling you, you're not going to be tested on, but I'm trying to see if maybe if I explain it this way, it'll make more sense to you where the whole idea comes from, all right? And it's how we get to what's called the fundamental theorem of calculus. That's like it's a fundamental theorem of the subject of calculus. It's a huge theorem. So bear with me. Let's see how this goes, all right? I want you to ask questions. Y'all are my beta group here. I'm beta testing on you, okay? So if something doesn't make sense, you're going to need to let me know, all right? So to get this motivated, this is where we're going to try and get to. To get it motivated, let me turn the lights up a little bit here. I need you to remember something from Cal 1. Whoa, geez. I need you to remember something from Cal 1. It was a theorem in Cal 1 that you covered, and you may or may not, depending on your professor, may or may not have stressed it, but I'm sure you saw it, all right? Because you can't get out of this class without seeing it. It's called the mean value theorem. Sound familiar? MVT, mean value theorem from Cal 1, yeah? Let me remind you what it is, all right? The mean value theorem says this. I'll write the actual theorem up here on the board in a second. Let me show you geometrically what the mean value theorem says. The mean value theorem says if you have a continuous function on a closed interval, so do y'all see this green function? It's continuous, right? I can draw it without picking up my pencil. And it's defined on a closed interval, which means it has a solid point here, draw it, solid point at the end. That is a continuous function on a closed interval. So let me write that down here. Mean value theorem says if you have some function f is continuous on a closed interval AB, okay, which it is, right? That is a continuous function on a closed interval. And f prime exists on the interior of AB, which means that inside of here, you can take the derivative and it exists. So at every point in here, we have a slope of a tangent line, right? That's what the derivative is, slope of a tangent line. So everywhere in here, the derivative needs to exist. If those two conditions are true, okay, so this is the assumption. We assume that part of it. So if that's true, what's the result? The result says, for the mean value theorem, that if you connect the, oh shit, too much stuff, sorry. If you connect these two endpoints, if you connect the two endpoints with a straight line, right, that black dotted line, that black dotted line has a slope to it, right? That black dotted line has a slope. Now let's see what that slope would be. What would the slope of that line be? Well, what's the slope of any line? Rise over run, right? Rise over run. So the rise would be the change in y right here, right? And the run would be the change in x. That would be the slope of the black line. So I'm going to write that down over here. The rise, let me write it down first. Over run, oops, wrong way. So remember, I'm calling this left endpoint A, and the right endpoint, I'm calling it B. Do you all agree that the distance from here to here would be B minus A then? Whatever this is, B, take away A. That's B minus A. That's your run. That's the bottom. The rise is the difference in the y coordinates. That top y coordinate is f of b, and the bottom y coordinate is f of a. Understand? So rise over run. The mean value theorem says that the slope of that black line should be equal to the slope of the tangent line on that graph somewhere in there. So in other words, somewhere in this, on this curve, I should be able to find a point somewhere where those two lines are parallel. What does it look like? Am I there yet? Where is it? I have the computer solve it for me. It's 3.21455. So 3.215. I'll just go with that. Do you all agree by looking at that the red line has a slope that's equal to the black line there? They're parallel, right? So the mean value theorem says as long as you've got a continuous function on a closed interval, as long as the derivative exists, then the slope of that black line should be equal to the slope of the tangent line at some point in there, right? At some point. We're guaranteed there's some point in here where it happens. We call that C. So right here, this C for us is what? On this particular graph, it's about 3.215. Does that theorem look familiar to you? The parallel line thing? Yes? Okay, let me recap. You give me a continuous function on a closed interval. I connect the two endpoints with a straight line. There should be some point between here and here that if I go to the original graph, and draw the tangent line at that point, we should have parallel. Okay? Believe it or not, that theorem is what allows us to find the areas under curves. And it doesn't seem like it should, but it does, all right? Okay, are we okay with this? Can I leave this alone? Yes? Okay, we need this though, but just, if there are any questions, now's the time. Okay.
Can that be restated with like delta y over delta x? Like
Yes. Yeah, this is change in y over change in x, right here. But in terms of the mean value theorem, you're given a function, right? So you actually know what the change in y is. The change in y is just the difference of the y coordinates, right? You understand these are the y coordinates of the points.
Yeah.
And so this is like y2 minus y1 over x2 minus x1. So rise over run.
Okay.
Yeah? Okay. All right. So what I'd like to do now, and right now you're not going to know why I'm doing this, so you're just going to have to believe me on this, all right? And just go with me. Like I said, I'm beta testing here. If I change this theorem and I call this little f capital F instead, no big deal, right? I'm just calling it capital F, right? And then this right here, I want this to be the derivative of that capital F. All I'm doing is changing the notation, that's it. And then right here, this would be the derivative of capital F. And this would be big F, like that. That's the same theorem, isn't it? Same exact theorem. I just used capital F instead of little f. And now I want you to recall that when we started using capital F, the relationship between capital F and little f was this, that the derivative of capital F was little f. Right? So when we were finding what's the antiderivative of this? Some capital F, right? So if I take the derivative of that capital F, I should get little f. This is a relationship we had established before. Okay, so if I write it this way, right, then what can this be? How can I rewrite this instead of f prime? What could I put here? Little f, okay, and instead of this, I could put what? Be careful here. What is it? F of c, not f prime, little f of c. This could be rewritten with f of c. So if I have some capital F function, so imagine the green is the capital F now, okay? The green is the capital F. Then, as long as that's continuous on a closed interval, then the derivative of that capital F, which we're calling little f, that needs to exist on that interval, and then here's the relationship we have. The derivative of that function at c must be equal to this ratio. All right, I'm going to use that now, all right? I'm like in uncharted waters here, okay? So I'm just trying to figure out the path I want to go through this. I need more board space. Let me do this. I'm going to put this over here. I'm just going to put this over here. What we have is that f of c must equal capital F of b minus capital F of a over b minus a. And just remember, this is for some c. We don't know what it is yet, but for some c. Okay, so there's some c in there where those things will be tangent. Now, we good? All right. Clear your minds for a moment. Clear your minds. And let's start with the area problem again. Okay, let's go back to the area problem. Let's say that I have a function here, little f. Okay? Just some function, little f, right? And I would like to know between a and b what that area underneath this is, right? I'd like to know what that is. Okay? I'm going to show you a picture of what I just did up here on the screen. So let me get this out of here. We're starting over from scratch. We're not even thinking about that anymore. I've just got some little f right here, right? I've got some function little f, and I want to know the area underneath it, right? Okay. Well, do you agree that if this little f exists, then we should be able to find its antiderivative, right? Hopefully. And the antiderivative would be a different function, wouldn't it? So over here on this graph, I'm going to do a separate graph, and over here I'm going to graph, it's going to be not necessarily the same as that graph, but this is going to be capital F, all right, at A and at B. There it is. Now, I'm not looking for the area under this, right? I'm looking for the area under this. Agreed? So, how do we do it? Well, we just talked about the mean value theorem on this, didn't we? What did we say the mean value theorem told us here? It's right there. It says that little f of c, right? What is little f? Little f is the derivative of that, right? Which is graphed over there. That, there's some c where that is equal to capital F of b minus capital F of a over b minus a, right? That's the mean value theorem. Y'all still with me? Okay. Remember, we want this area, now I'm looking at that. This is the part that's like, okay, whoa, would have never thought of this. Take this and tell me if you agree with this. Tell me what I did algebraically here. It's a pretty simple step. What do I do? I multiply both sides by b minus a, right? That's legal, right? Okay. I want you to think about what this is saying. Remember, there's some c in here, somewhere in here, right? We don't know where it is. That if you connect this together, right? There's some c, I'm just going to say about right here. There's some c right in here where that slope of the tangent line is parallel, yes? That c lives between a and b, right? What is this? What is this? What is f of c minus b minus, sorry, f of c times b minus a? Well, what's b minus a? It's the difference, it's this distance, isn't it? Right, it's this distance. What's f of c? Little f of c. What's little f of c? Well, it's just the value, that point right there, bring it over here, right? C, isn't that just the value of the function right there? That's the height, and then this right here is the what? Width of that thing, right? So do you all see that this red box right there, the area of that red box is this side right here. Geometrically, that is height times width over here, isn't it? Now I want the area of the green. Is the area of the red equal to the green or no?
Not quite.
Not quite, right? They're off a little bit. This goes straight across this. The red goes straight across, the black has some undulations. But would you say that that red's a pretty good approximation? Yes? And what is the area of that box? Well, let's see. What is the area of that box? It's this, what's capital F of B? That's, it's the height of the right endpoint, right? It's this height, that height is capital F of B, and capital F of A is what? The endpoint, the height of the endpoint, there. So this is saying that if I want to know the area of the red box, all I need to do is go look at the antiderivative of that function, evaluate the antiderivative at the right endpoint, get that answer, evaluate at the left endpoint, get that answer, and then subtract, right? Subtract. And that will be equal to the area of the red box. Now, we said it's approximate, right? How could we make it better? Don't say more rectangles, because that's not what's going to happen. Let me see. I want to come over here to my picture. Let me put my stuff in here. There we go. There we go. So the problem with this, I can't have two pictures at the same time. So the picture you're looking at here is this one right here, right? The red box, right? To find the area of this red box, what I need is to look at the antiderivative and then look at the two endpoints and just subtract, right? But it's an approximation. How do I get a better approximation? Hold on. What I do is I don't look at the entire interval, right? I was looking for the area under the whole thing, right? What if I just start first by narrowing everything down to some infinitesimal little tiny little section, right? Let me zoom in on this. Okay, so instead of trying to find the area of the whole thing, right? The whole thing, what if I just try and find the area of a little sliver? Do you agree that the red is still not the blue, right? The red is still off. But do you agree that that error is now really small, right? Really small. And could I find that? On that little tiny interval, could I approximate that area? Yes. And then could I move to another little tiny interval and do it again? And then do it again? And then do it again? And do it again? Add them all up? Yes? Y'all see that? How small can I get? Infinitesimal, right? Like take a limit. Let that width go down to 0, basically. And that would give you like an infinite number of little sections. So let me see. I don't think I can go any further. I can go pretty far. Oh, shit. Right there. So I'm zoomed in pretty good here, right? Do you understand the concept? Okay. This is the part I thought this far ahead. When I came in, I was like, I'm going to go try this. This is where I thought to. So the rest of this is I'm just going to be seeing if I can put it together now. All right? Do I need to recap it all? One more time? No? Okay, no. All right. All right, so I'm going to get rid of the projector. Got to do this. Because this part's I think, going to be the kind of like the mind-blowing part. All right. So here's what we're going to do. I'm going to go back to this picture here. And instead of doing one big rectangle, I'm going to start doing a bunch of little ones. Okay? And when I do that, it'll look something like this. Let's still start here at A. Let's still go to B. And let's do that, right? And now I'm going to take this tiny, tiny, tiny little interval. Now, because it's infinitesimally small, but just so you can see it, I'm just going to make it right here. Okay? So instead of going from A to B, I'm now going to go from A to, let's just call this B1, okay? B1. Now what I could do is now I could go look at that, right? I could go look at the antiderivative over here, and I could look at that same little interval, couldn't I? And then for that interval, I could use the mean value theorem, and I would get some C, wouldn't I? For that little interval. So in here, I would get what I'm going to call C1. And then that would draw me a little rectangle in here, wouldn't it? Like that? Yes? Okay, what is the area of that rectangle, the red one? What's the area of that? In terms of this guy? It would be this one, right? It would be this. But we have to use the endpoints we have here. So, look, what's the area of this one? The area is, tell me, capital F of B1 minus capital F of A. Understand that? By the mean value theorem, by this theorem right here, that would be the area of that first little rectangle. Got it? Now, let's look at the next rectangle. Now I'm going to go from B1 to, let's say, B2. And I draw another rectangle. Oh, wait, I need the C, right? So I do my mean value theorem. I'm going to get a different C for that little interval. This will be, let's say, C2. And then I go up and I draw a different rectangle in there. What's the area of that rectangle? Capital F of B2 minus capital F of B1. Following? What about the next rectangle? If this is B3, that area would be what? F of B3 minus capital F of B2. And do you all see I just keep doing this for as many rectangles as I have? Yes? Okay, let's get to the last rectangle. The last rectangle, I don't know how many I have, do I? I don't know how many I have, but let's just call this one B sub n. I don't know how many, however many it is, right? So what would the area of this last rectangle be? Capital F of B minus capital F of B sub n. Right. Okay. I hope you're following me. So what is the total area then? If I add all those up, let's see what happens. This is going to be the part that's, I think, going to be awesome. Let's start adding them up. So the first one, right? I take that one, which is, so the area is going to be equal to capital F of B minus 1 minus capital F of A, plus, now the next one, capital F of B sub 2 minus capital F of B sub 1, right? Plus, now the next one, capital F of B sub 3 minus capital F B sub 2, yes? Plus, and now I keep doing this, dot, 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 plus, and then I get to the very last one, capital F of B minus capital F of B sub n. Do y'all see what happens? What happens? A bunch of shit cancels, right? What cancels? This cancels with this, right? This stays, right? That cancels with that, right? Does this stay? No, this one's going to cancel with what? Something in here, right? And isn't everything in the middle going to kind of just all cancel out? Until you get to the very last one, what stays, what goes? Does that stay or go? Stays. Does that go? That cancel with the one that was in here, right? There's one right before this that would cancel this one, right? So what's left? Capital F of B minus capital F of A. And so amazingly, if you want to know the area underneath some curve little f, from A to B, if you want to know that area, amazingly, all you have to do is calculate what the antiderivative is, and then evaluate it at the two endpoints, subtract those answers, and you're done. And this is what's called the fundamental theorem of calculus, all right? Now, I am kind of like weaving my way around a few little technical issues here. Like I said, n rectangles, we actually need an infinite number of them, okay? We need an infinite number of them. So we need to do a limit. We need to take a limit and let n go to infinity. I'm not going to get into that, all right? This is more, do you understand the idea of how